So our last topic then on medical physics is on ultrasound. Now, hopefully you already know a little bit about what ultrasound is. It's the name we give to sounds that have a frequency of higher than 20,000 hertz. It's too high pitched for humans to hear, which I would call it ultrasound, but there are animals that can hear ultrasound. So dogs, cats, bats, moths, things like that can hear it. So why do we use it in medicine? Most common one you most likely know, is for checking the condition of a fetus. We also use it to look for liver problems, to look for heart problems. It can also actually be used to treat kidney stones. So we can use the ultrasound to vibrate the stones to break them down so that they can be removed from the body naturally. Also use it to measure the speed of blood flow in the body. So ultrasound is actually very, very useful. It's also one of the most widely used types of scanner because it's very portable, it's quite cheap, and you can use it for a lot of different things, which makes it very, very handy. So how do we produce this ultrasound? Well, we both create and detect ultrasound using the same principle and using the same wand. So the wand that they use to do the ultrasound with both creates and detects it, and it uses something called the piezoelectric effect. So what is that? Basically, piezoelectric materials have special properties. When this material is in rest state, the ions are all arranged so that the charges are geometrically symmetrical. So basically it has no charge. If I then stretch or compress the material, the ions are moved and it causes a potential difference to be formed. So instead of them being evenly dispersed, so there's no overall collection of charge, once I squash it or I stretch it, those charges shift so that there is a potential difference, there is a banding up of the charges. And if I squash and compress and bounce it backwards and forwards, what I find is that positive and negative flip sides. So I can make an alternating potential difference by vibrating this crystal. So in the ultrasound, what we do is, if the crystal is vibrated and an alternating voltage is then produced, that's how I detect the ultrasound. So the ultrasound wave vibrates the crystal, which produces an alternating voltage which I can detect. So that's how I detect it. So in order to produce it, I just do the opposite. I apply a voltage to the crystal, that makes it change shape, and as it changes shape, I can make it vibrate at the frequency for the ultrasound, and there we go, I've produced the ultrasound. So it's actually quite a it's a very elegant solution, really, and it's quite a nice application of physics there. So how do we produce these images then? Well, first of all, we send the ultrasound into the patient's body. At every boundary in the patient's body, some of the ultrasound is reflected and the rest is transmitted. We can calculate how deep the layer is by looking at the time it took for the sound wave to return after it was reflected. So basically the same as the way that sonar works. And then we typically process the waves and use them to produce an image of the body. Now there are two types of ultrasound scan that are often used. There is an A scan, which stands for Amplitude Scan, and this basically is measuring how far away all the boundaries in the body are. And we do that by recording the time it takes for the wave to travel there and back, and we measure that using a CRO, so a cathode ray oscilloscope. And any time that the wave hits the surface, we'll see a peak in the trace on the cathode ray oscilloscope. And this is often very useful for measuring how far apart two boundaries are. So it's often used for measuring, say, the size of the fetus's head so that you can figure out how old it is and if it's developing healthily. Second type of scan is a B scan, which stands for brightness scan. Now, a B scan is basically a combination of lots of A scans taken from different angles. And all we do is combine all the peaks that we would have gotten on the A scan and combine them together into points of brightness to build up a picture. And that can give us a two-dimensional image of what's happening inside. So the B scan is a combination of lots of A scans from different angles. So why is it that we're using ultrasound? Basically, it's because, and particularly we use this for looking at babies, because the ultrasound can have very small amplitudes, so that means that the waves are very low energy, which makes it safe because it's not going to damage the living cells, which obviously if we're looking at babies we very much don't want to do. In a lot of cases the alternative would be using X-rays, and those would be high energy, and that can damage cells. Now the other thing about ultrasound is that I can alter the wavelength slightly, which allows me to change the size of things that I can see, because obviously I want my wavelength to be similar to the thing that I'm looking at, because that would allow me to see more detail of what's going on. Now the other thing that I said we could do is measure the speed that blood is flowing in the body, and we do that using a Doppler ultrasound. Now we already talked about the Doppler effect fairly recently, so this should be quite fresh in your minds. And what we do here is the ultrasound wave reflects off the moving blood cells. That allows us to then check how fast the blood is flowing. And it's often a useful thing to do to see how fast blood is going to the brain, because it can give you a warning signs if there's going to be a stroke in a patient. So it's very useful. So the exact way these Doppler scans work is that we place the transducer at an angle to the artery, and the ultrasound that gets reflected off the moving blood cells, when it returns to the transducer, it has an altered frequency. And the change in frequency is directly proportional to the speed at which the blood is moving, so I can then calculate the speed of the blood. Okay, so next thing we need to talk about with ultrasounds is something called attenuation. Hopefully you'll remember that attenuation is about how the rays lose energy as they pass through materials. And for the ultrasounds, the way they lose energy is by getting spread out, by getting scattered, or being absorbed by the material. Now we're interested in the absorption by the medium. The scattering and spreading out is less interesting. So how much gets absorbed depends on the medium. So water absorbs very little, bone absorbs a lot. Now what that does mean is that if you are not careful with your ultrasound and you point it at bone, because it absorbs a lot of the energy, you can actually end up damaging bone with ultrasound, so you do have to be a little bit careful. The other thing that we need to consider is the frequency of the wave, because higher frequency waves are more easily absorbed. Now, you may know this from life experience, because if any of you have got older brothers or possibly younger brothers or sisters that like to play music quite loudly, you may notice that you can't hear the melody through the walls, but you can always hear the thud of the bass. And that's because the high frequency melody doesn't come through because it gets absorbed by the wall, whereas the lower frequency bass sounds don't get absorbed as easily, which is why they make it through. In terms of medicine, that basically means that you need to pick the frequency that matches the thing that you're looking at in the human body. Okay, so impedance then. So we said that materials tend to resist the passage of sound, kind of like resistance of components and circuits. And different materials have different acoustic impedances. And we can calculate that acoustic impedance by doing the density times the speed of sound moving through it. So note that C there. This is an instance where we're using C to mean wave speed, not the speed of light, because it's sound we're talking about, so it would be very weird if you then put in 3 times 10 to the 8 here. Yet some of you probably will, so don't. All the impedance is a measure of how the molecules move in response to the sound wave. It's not really about how much energy is lost, it's just how easy it is for the wave to pass through that material. So just to give you some idea of some impedances, here are some values. So air is about 430, skin is 1.35 times 10 to the 6, fat 1.38 times 10 to the 6. Notice how the ones in the body are all very similar and air is distinctly different. That is going to be important because the difference is going to determine how much of the ultrasound intensity actually makes it into the body. So at every boundary, I said that some ultrasound is reflected and some is transmitted. Now, obviously, we need some to be reflected at boundaries so we can see what's happening, but we need some to keep going so that we can, look inside the body. So if I want to find the fraction of reflected intensity, so the intensity that's reflected divided by the intensity that I put in, so how much actually goes through a boundary, I do Z2 minus Z1 over Z2 plus Z1 squared. So if we just have a little look at the ratio of reflected intensity between air and skin, if I put those numbers in, it was 1.35 times 10 to the 6 minus 430 divided by 1.35 times 10 to the 6 plus 430 squared. That gives me 0.999. That number is a big, big issue. My question is, why? Remember, this is the boundary between air and skin, and I've just said that 99% of the ultrasound is reflected at the boundary between air and skin. Well, that means then that none of the ultrasound made it into the body, so it's not going to be able to tell me about the body. I've got 1%. That's not going to give me a very good image, is it? So, if we did nothing, very little ultrasound would get into the body. So to solve this, what we do is we use a coupling gel. So we put that, I'm sure you've seen in movies where before they do the ultrasound they squeeze on the gel and then put the transducer into it. So that is the coupling gel. And the coupling gel has an impedance that's very similar to that of the skin. So that matching is called acoustic impedance matching. If the numbers are very similar between the gel and the skin, when the wave passes from the gel to the skin, we don't get much reflected. So we actually manage to get more of the ultrasound into the patient's body so that we can in fact then see what's going on inside. Okay, so that is ultrasound. That is it for medical physics, and that is actually the end of the topics that you will be doing with me this year. So, revision time. Remember, any questions, ask when you see me, and make sure that you are revising in earnest after this point. Okay.